what happened in the system itself. Please, can he rejoin? What is the, why did it happen? Meanwhile, something happened. Someone was removed from the meeting, I don't know, due to technical reason it was removed. Okay, Arghadip, so you can send a message to Atita and to send me the request again. I don't know why it happened. Okay.
Sir, yes sir, I am asking him to join again, but I don't think he will require your permission again.
Okay, okay.
You have already...
Arghadip, what you answered is correct. Acha, Niladri, do you want to say something? You were about to say something.
Sir, আমি এটাই বলতে যাচ্ছিলাম স্যার, ওই কাইনেটিক এনার্জি ট্রান্সফার করার ব্যাপারটা মলিকিউলার ভাইব্রেশনের থ্রুতে।
Sir, basically someone Arghadip probably he talked about solid and
conduction can take place in all three, liquid, solid and gases too. Sir, it is the mode of energy transfer where energy is transferred without the actual movement of the particles in the medium.
It happens in stationary media. Can you say that in conduction?
No,
conduction stationary media. When the medium is stationary.
No, sir.
So without the actual motion of the particles, the heat is transferred.
So when there will be no fluid movement with respect to solid, or say we are considering a stratified fluid. Stratified fluid means, say I have fluid, upper layer is at hot temperature, lower is at cold temperature. Okay. Under this situation, you will find no convection will set up.
Yes,
here
sir.
the heat transfer will be conduction from the upper layer to lower layer. Have you understood?
Yes sir.
So even through liquid also it may conduct. Okay. Another thing is, say in conduction, if I like to ask you what is the purpose of studying conduction? As a thermal engineering student or mechanical engineering student, if someone asks you why did you learn conduction heat transfer, what did you learn? Can you answer? What is the objective? What you are saying is definition. If I ask you what is the objective, can you express in simple words?
Sir, conduction
Sir, we
can
have
be used to measure the temperature at any places, because maybe temperature at places which maybe human cannot insert a thermometer or something. So we can...
Okay, very good answer. Obishek was about to say something. Very good
Sir,
answer.
we can, sir, to increase the effectivity of machines and other equipment, sir, because the natural way of heat energy loss is in the form of heat. So if we study heat transfer, we can actually play with it. We can, in required places, we can increase the heat efficiency, the heat loss. We can increase or decrease the rate of heat transfer based on our requirements, sir.
When you talk about heat loss, it comes about convection. Okay.
Sir,
So basically, Somnath, you were about to say something.
Sir, through conduction we can determine the temperature inside the metal, so that is a very helpful thing. But
Yes, the purpose of, if you have studied the conduction portion, you will find in the conduction whatever you have learned, here H is specified, boundary condition or heat loss condition. These are specified. Now what happens? You determine the temperature distribution as a function of space and time. Space and time means for steady state device or steady state system, temperature doesn't change with time. So here, one way that under steady state, what will be my temperature distribution in the solid? Suppose you are designing a electronic equipment. Here, what is the criteria in any electronic or semiconductor device? The criteria is the temperature should not exceed approximately 100 degree. Okay, approximately 100 degree. Now you are a thermal engineer. You are asked to design a electronic component from thermal perspective, such that you have to choose the material, you have to choose the system in such a manner that the temperature doesn't exceed beyond 100 degree. Now here one objective is to design it in such a manner that temperature doesn't exceed a specified. Now temperature, now here you have to identify where will be the maximum temperature location. Maximum temperature location in isolation you cannot determine. You have to consider the whole domain. Either you can solve it analytically, numerically or experimentally. Now experimental point, Arghadip pointed out, sometimes it may not be possible to access all the points in a system. So here if I can apply conduction heat heat equation, conduction equation, okay, along with proper boundary condition, if we can analytically predict, we can numerically predict, okay. If it is a non-linear system, say we have to predict for numerically, we cannot go by analytical method, okay. So here the purpose is, you will find that in conduction heat transfer, when you analyze the conduction system, boundary condition or convective condition is specified, okay. Have you observed this?
Yes, sir. Sir, we need convection in order to
Yes, sir.
find out the temperature at two surfaces.
Exactly. Now, another example I am giving you. Suppose you are designing a nuclear system. In the nuclear fuel, say UO2, uranium dioxide fuel, you are. Now here there is heat generation. Now you know heat generation term is there. So source term is there. You will approximate the fuel rod as a cylindrical geometry. Then you apply the conduction law with the heat generation term. You find the peak temperature location and make sure that it should be within the specified limit, it should be less than melting point, and it should not reach a point where the temperature is beyond a specified limit. Okay, so more or less, in simple words, and another point Abhishek pointed out, another thing, like fin, in this class we will discuss about fin, and some of the aspects we will discuss before starting the experimental setup and experimental procedure. Coming to fin, what is the purpose of using a fin?
স্যার হিট ট্রান্সফার রেটটাকে বাড়ানোর জন্য স্যার।
Both increase and decrease.
Managing the stability
transfer
of
rate
the
টা
system.
Sir, heat transfer rate can both increase and decrease using a fan.
Yes, Abhishek, very good answer. Whether fin is effective in a situation, how will you determine? A situation is given to you, that fin, as Abhishek answered, fin may increase heat transfer, fin may decrease heat transfer. Okay. Now, whether we should apply a fin,
স্যার এইচ এর ভ্যালু যেখানে কম থাকবে অ্যাকচুয়ালি, কারণ এইচ এর ভ্যালু স্যার যদি বেশি থাকে তাহলে আমাদের এফেক্টিভনেসটা কমে যায় ফিনের স্যার।
very good answer. Very good answer. Sometimes this is asked. There is a tubular heat exchanger, okay? Imagine a tubular heat exchanger, tube and cell type heat exchanger. One side there is gas flowing, hot gas flowing, another side there is some liquid flowing. There is a heat transfer from gas to liquid. Now, suppose there are tubes. You want to put fins in the outer surface or inner surface. By some technique. On which side you will put the fin, on the gas side or on the liquid side?
স্যার গ্যাস সাইড স্যার।
Very good answer, Niladri. Do you agree? Everybody agrees. Why gas
Yes,
side?
sir. Yes, sir.
স্যার কারণ এইচ এর ভ্যালুটা স্যার গ্যাস সাইডে স্যার কম, আর লিকুইড সাইডে এইচ এর ভ্যালুটা বেশি, তো স্যার এফেক্টিভনেসটা বাড়বে যদি গ্যাস সাইডে পুট।
Fin effectiveness is defined. You calculate a situation, you imagine a situation when you apply the fin, approximate that solution, try to find out the effectiveness. If effectiveness is greater than 2, at least greater than 2, then fin is effective. In fact, it should be at least 5 or 6 or as high as value possible. If it is less than 2, the fin is said to be ineffective. And fin may be detrimental, even detrimental. Okay. If you get a very low effectiveness. Have you understood?
Yes, sir.
Yes, sir.
So, coming to convective heat transfer. What is the objective of studying convective heat transfer? Single sentence. I require a single sentence. Elaborate analysis, no elaboration. Single sentence, can you identify the objective?
Sir, understanding energy, heat transfer.
No, that is not a simple answer. Anybody? Niladri?
Sir, thinking about the stability of a system.
No. I need a solid answer. Determination of H. Determination of H. Determination of heat transfer coefficient. Sole objective of convective heat transfer. If you find The main objective or main focus is H. Now relate with what we were discussing. In conduction heat transfer, what we study? With a specified H, we solve for temperature distribution. In convective heat transfer, depending upon different flow like laminar or turbulent, like forced convection or natural convection, we analyze the situation and determine H either by experimentally or by analytically or by numerically. Is it clear to everybody?
Yes, sir.
Yes, sir.
Okay. About radiation we will discuss later. Okay. Now, determination of H and how to increase H. You know, heat transfer enhancement is a huge subject. How we can increase H by increasing turbulence. Like in heat exchanger, we put baffles. You know, baffles can increase the turbulence and mixing. So, use of baffle can increase H. Okay. Now, one may ask that what is the penalty? Can anybody say what is the penalty? You understand the meaning of penalty? We are trying to increase H by increasing heat transfer, by increasing Reynolds number. What could be the penalty for this? Can anybody answer? Think about fluid mechanics. Acha, if we can increase H, what is the advantage? Anybody? Somnath, I am asking you. Somnath, you can answer.
Yes.
Feel free to answer. If we can increase H, what is the advantage? Can anybody answer?
The heat transfer would be in greater rate.
Okay, heat transfer will be better. Fine. From design perspective, anybody can answer?
Sir, we have to মানে এরিয়াটা কম করতে হবে
এরিয়াটা কম লাগবে।
হ্যাঁ
For same heat duty, H A delta T. So if you can approximate delta T as the mean temperature difference, like LMTD. Okay. So LMTD, if you delta T remains same, if you can increase H, A will be less, area will be less. Area will be less means design will be compact, capital cost will be decreased. Okay.
yes
Similarly, if you put baffles, H will increase, area will be compact. What is the penalty for that? Abhishek?
Sir, like in
Sir,
fluid
head
mechanics-
loss টা কি
Exactly, Niladri. Exactly, Niladri. Head loss বাড়বে, pressure drop will increase. If pressure drop increases, what happens to pumping power?
to increase the pumping power.
decrease, sir.
U delta P. U delta P. You are increasing delta P.
Sir, Q will be reduced, sir.
Q will not be reduced because if you try to increase increasing H by increasing Reynolds number means flow rate will increase. Flow rate will increase. It will increase Q. Now, if you put baffle will increase the heat transfer. But what happens if area gets reduced? Pressure drop will increase. Inversely proportional to diameter. Now, what is going to happen? There is it is an optimization problem now. You have to go for a design. You have to go for a design where you have to seek a trade-off between these two. One will increase your capital cost by reducing area, but at the same time pumping power will increase, so pumping cost will increase. Now it's a problem of cost optimization. Have you understood?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
So as you see, what you have studied in your heat transfer course has something to do with real life engineering problems. Okay, and there are many more subjects related to this where you will find this kind of application, and where from the first principle you can answer, but for a better answer you have to go for experiment, you have to go for analysis. Okay, further analysis like this. So now let us start the experiment. So here in this laboratory class we have total 6 experiments will be covered. 3 from conduction, 2 from convection, 1 from radiation. So conduction, the first experiment will be on fin. The second experiment is determination of thermal conductivity. So one thing is that using the principle of conduction, which I didn't mention, using the principle of conduction, you can measure the thermal property. Like if you want to measure thermal diffusivity, for example, thermal diffusivity, what is the meaning of thermal diffusivity? What is the unit of thermal diffusivity?
Sir, it's K by rho C. No, I have to-
Unit meter square per second. Meter square per second. Okay. Alpha. K by rho Cp is alpha. If you resolve the unit into the least level, you will get L square T minus. Okay. T minus 1. L to the power 2, T to the power minus 1. Okay. Meter square per second. Now say if you have a setup where you can find the temperature distribution as a function of space and time, from that there are techniques that you can determine the thermal diffusivity of a material. Similarly, if you can apply a thermal steady state situation, you can determine the thermal conductivity of an unknown material. Okay. So using the principles of heat conduction, sometimes we can determine the thermal properties, okay, or transport properties, okay. We have two experiments on convection, one on forced convection, another in natural convection, okay, that we will discuss again. What is the difference between forced convection and natural convection?
Sir, in forced convection, flow of liquid is forced actually.
Liquid or fluid?
Fluid, sir, by fan or something.
In natural convection?
Sir, the flow of fluid is natural here.
Natural means?
it's a density-driven flow.
Temperature to density difference, yes, sir.
Density difference. Buoyancy.
Buoyancy difference. Density difference. Okay. So, in forced convection and natural convection, if you can express the... Achha, have you done the non-dimensional number? Have you studied about non-dimensional number? Non-dimensional numbers, Reynolds number,
Yes, sir.
Prandtl number,
Nusselt number and all.
Nusselt number. What is the use of these numbers? Why these numbers are studied? Do you have
So
any
they
idea?
can be treated as flow parameters, like conduction case or H can be treated as a function of Reynolds number and Prandtl number. The Nusselt number is basically HLS by K. So
Why it is done?
सर एगुलो जेहेतु सर नॉन डायमेंशनल बाउंड्री कंडीशन से सुविधा होते पड़े एक्चुअली
ना. Have you studied about geometric similarity, kinematic
Yes, sir.
similarity? Huh?
yes, sir.
What is that? Why that is studied?
Sir, actually, we can develop a formula or a suitable condition for a small prototype, and then you can use it, extend it to larger objects of the same type. So we can study for.
Exactly. So, if you try to develop, say, a huge system, you can scale down by scaling down the geometry. Okay. Now, if you want to understand the phenomena, see, geometric similarity means all geometric parameters are there. They have model and prototype has certain ratio of the primary dimensions. Okay. Kinematic similarity means if you see the flow field of the model and the prototype, at each and individual point to point wise, you will have the velocity ratio will be same, or the streamline will have the similar. This is geometric similarity. Then dynamic similarity is something the Reynolds number will be the same. Okay. Thermal similarity is when Nusselt number will be same. Now why this is done? This is done because two things are there. First, understand. Suppose a flow is taking place in a pipe. You want to parameterize it. You want to say study the heat transfer coefficient. Now if you want to understand the phenomena as a function of different variables, how you will express? You will first vary the diameter of the pipe, then velocity of the flow, then viscosity of the fluid, then so many parameters are there. Okay, density of the fluid. How many parameters? Rho, V, D, mu, then Cp, K, all these things. Prandtl number means basically mu, Cp, K, all these will come into picture. Now, individually varying these parameters to understand the phenomena is cumbersome and it is very difficult to characterize. It is observed that if you can put the Reynolds number same, the flow characteristics is same. And for this, you have to non-dimensionalize the equation. You will understand. If you non-dimensionalize the equation, these parameters will appear in the governing equation itself. Now, what does it mean? If I can keep Reynolds number same, I will get the same flow characteristics. Now, we express heat transfer coefficient as a non-dimensional number like Nusselt number. Now we say Nusselt is a function of Reynolds number and Prandtl number, 2 parameters only. If we had to see the H as a function of so many parameters, we have to do the analysis. So it was a function of so many parameters and becomes cumbersome. And if we can maintain the geometric, kinematic, dynamic similarity, then what happens? We can design a system very comfortably, and if the phenomena is true for the model, it will be true for the prototype also. Have you understood?
Yes, sir.
So, what is the significance of Prandtl number? Is it a property?
Sir, it defines the rate of cooling of a system, no, sir?
Prandtl number, no.
So it is some kind of ratio between some thermal diffusivity and something, no?
Momentum diffusivity and thermal diffusivity.
Yes, sir. Yes, sir.
Actually, when you study the boundary layer flow, you will understand this. Prandtl number determines what is the boundary layer ratio, thermal boundary layer to hydrodynamic boundary layer ratio. So you will find that the thermal diffusion is predominant or momentum diffusion is predominant. Like a Prandtl number, high Prandtl number, like oil, very high Prandtl number. Water, something like varies from 6 to 10, 6 to 10. High but not moderately high. In this case, you know, momentum boundary layer or hydrodynamic boundary layer is higher size than the thermal boundary layer. Okay. So momentum diffusion term is dominating. Low Prandtl number like liquid metal. Very small Prandtl number, 0.02, something like this. Okay. Or even less than that. Here the thermal diffusion is prominent. Okay. Thermal boundary layer is basically your thermal boundary layer is much higher than the momentum boundary layer. Okay. So these are the some of the things which we have studied, and heat exchanger you have studied. Radiation heat transfer we will discuss before the radiation experiment. It will be better to discuss. Okay. So we will start the first experiment. Let us go to the presentation. You have watched the video, right?
Yes, sir.
Yes, sir.
So, the title of this experiment is heat transfer from a pin fin. You know, there are different kind of fins, okay, of the different cross sections. So here we will discuss about a pin fin, and the objective, first objective, to find out the rate of heat transfer and heat transfer coefficient through a pin fin. Second objective, to study the temperature distribution along the length of the pin fin. Okay. So again, you can determine the fin effectiveness or fin efficiency from this also. Okay. What is the fin effectiveness? In addition, I would suggest you to, if you try to determine, you can determine these two parameters also. Okay. So let us recap about some background theory. You don't see the red part first. First, let us go the conventional part. You know, if this is the x direction and this is the length of the fin, and you know the fin is attached to this wall. This is the length, and the for one-dimensional fin with insulated tip, if we consider the tip as insulated, you know the incremental temperature, which is the temperature T, and ambient temperature is T infinity. This closed form solution is given like this. This equal to theta 0 cos hyperbolic m into L minus x by cos hyperbolic ml, where basically theta 0 is basically T minus T0, and theta 0 is T at x equal to 0. So this is called base temperature, T at x equal to 0. So T0 minus T infinity is specified. Usually in the fin analysis, this temperature is specified. So this is theta 0. And you know, L is the length of the fin and x is the local distance in the x direction. As a function of x, theta is expressed like this. And m is defined as basically root over hp by ka, m square equal to hp by ka. So if this is a fin, it is having a circular cross section. So here P is the perimeter and K is the thermal conductivity of the fin material and D is the diameter. So you will get this 4h by dk. If you expand P and A, you will get this expression. Now you see m square, it is dependent on so many things. H is flow characteristic, is basically dependent on the flow characteristics. K is the material properties and D is the geometrical property. Okay. Now this is the expression of theta. Hope I am audible and you can see the slide.
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir.
And you know the rate of heat transfer for this from this fin is root over hp ka tan hyperbolic ml. Since these equations were derived, I believe these equations were derived, right, in the class.
Yes, sir.
So now fin efficiency, how you define fin efficiency? Actual heat transfer by ideal heat transfer. What is the meaning of ideal heat transfer? Can anybody answer?
Sir, temperature will be constant, but base temperature will be there.
Temperature throughout the fin will be constant.
Throughout the fin.
Yes, sir.
Temperature throughout the fin will be constant, or fin will offer no thermal resistance.
Yes, sir.
Fin, when this temperature will be uniform everywhere, the base temperature, when fin will offer no thermal resistance. So now we have a fin has a thermal resistance under actual condition and we have zero thermal resistance, so which is the ideal condition. Now this is the heat transfer with actual condition by heat transfer under ideal condition. So that is the what you said, that fin at the base temperature. This ratio, if you see this condition, insulated tip condition, you will find this as the tan hyperbolic ml by ml. Okay. Now, first of all, this one, something which we can see from the first principle. For one-dimensional fin with insulated tip, what is the approximation for one-dimensional analysis? I hope you understand this. What is the meaning of one-dimensional analysis? Can anybody tell? One-dimensional analysis means?
Sir, all the parameters will vary only in a single direction. Sir,
It
single spatial direction.
means if I take a section here, say I am taking a section here, in this section, if I consider this section, in this section, if I say the primary variable as the temperature, this temperature is function of x only, along y direction there is no variation, right?
Yes,
Yes,
sir.
sir. Yes, sir.
Under what which condition we will get this approximation? What is the approximation for analysis?
স্যার বাকি দুটো ডিরেকশনে যদি লেন্থটা খুব বেশি হয়
না, শুধু তাই নয়, এখানে অ্যানালিসিসটা দেখাচ্ছি। Suppose, see on this figure, okay? Suppose this figure, I have said this is the center temperature of the fin. I am taking a section, right? This is the center line. Can you understand? This is the center line. This is the surface of the fin. Two surfaces of the fin. Now this is say my center temperature Tc, and this is say surface temperature Ts. Tc and Ts. Let us consider these are different. Tc is different than Ts, and say along y direction. Tc is the center temperature. Ts is the surface temperature, and T infinity is the ambient temperature. Now, see here, if I have an order of magnitude analysis, whatever is conducted from center to surface, if center temperature is higher, can we write K into Tc minus Ts by T by 2? Why? What is the order of magnitude of heat flux from this center to surface? Can anybody tell? Minus K del T del X, minus K del T del Y, right? Minus K into del T del Y, this is Y direction. Now what is minus K del T del Y? Can anybody tell? K into Tc minus Ts by T by 2. If this is the thickness is T, this is T by 2. Or say radius, you can think this about radius. I am consider about a rectangular fin. Say if it is radius, you can take R by 2. Say if it is radius, you can say D by 2. Okay. Forget about this, the dimension. T or maybe D by 2. If for a fin, it will be D by 2. Now this is K into Tc minus Ts by D by 2. This should be of the order of whatever is the energy convected from the surface. What is the heat flux convected from the surface? H into Ts minus T infinity. So if I equate these two, what shall I get? We will get Tc minus Ts by Ts minus T infinity is of the order of Ht by 2k. You can put it here Hd by 2k. Hd by 2k. Have you got it?
Sir, Hd by K.
Hd by K. Say Hd by K. Now what is that? This is nothing but bio number. See, H is the heat transfer coefficient. This is some dimension T or D. K is the thermal conductivity of the material. Now this is bio number. If the bio number is less than, if it is very small, what does it imply? If it is very small, what does it imply? It implies Tc minus Ts is much less than Ts minus T infinity. Isn't it?
Yes, sir. Yes, sir. Yes, sir.
Now what? Under the situation when bar number less than very small, when it is very small, it means the drop from Tc to Ts is small as compared to drop from Ts to T infinity. So under the situation, we can assume that along this direction, we have a little variation and our temperature will vary only on the X direction, not in the Y direction. Is that clear?
Yes, sir.
Yes, sir.
So see, like this kind of analysis, you can analyze this from first principle only. No equation is required. From first principle, you can arrive at this. This kind of analysis you have make a habit to do. Why some approximation, one dimensional, when it is justified. Now probably Niladri answered one thing, that when H is small, say bio number, when it will be small. So H should be small. See here, H should be small, K should be high, and T should be small. So what are the implications for this 1D heat conduction? It will be valid when heat transfer coefficient is low, but thermal conductivity is high. You will find the fin material, usually thermal conductivity is very high. Okay. Like copper, typical fin material. Okay. Aluminium. Okay. These are having high thermal conductivity. So under this situation, you will have this condition. Is that okay?
Sir, we have certain boundary conditions like infinitely long fin tip. Sir, in that case, we do not need to depend upon H and K. We can directly use it.
Why not?
Sir, in that case, we are assuming that the fin tip is infinitely long. So the value of T becomes very large, very small.
No, T is no, that is not a thing. basically L is largely small means after some time the temperature distribution will be asymptotic, but it doesn't mean that the energy principle will be lost. This analysis is still valid. It is irrespective of boundary condition, whether it is insulated tip, convective tip, or infinitely long. This analysis is still valid. Okay. That is something you are talking about, the only geometry. Now here there is a paradox. If you infinitely small means one dimension is negligibly small. It is not like that. It is some asymptotic solution. We can assume that kind of boundary condition. Okay.
Okay, sir.
Okay, should we proceed?
Yes, sir.
Yes, sir. Yes, sir.
Now here, one question: how to get H? Heat transfer coefficient, because unless you know H, you cannot solve this Q or theta, okay, because M contains H. So heat transfer coefficient calculated through correlation of dimensionless quantities. Look at this, dimensionless quantities. We are talking about non-dimensional number. Okay. For forced convection, Nusselt number is Hd by Kf equal to function of Reynolds number and Prandtl number. It is a sole function of two parameters only. Now see here, the beauty of this. When I am approximating Nusselt as a function of two parameters, it is very easy to correlate. If I express by H, solely by H to the individual parameters, it will contain so many parameters. Okay. So here what happens in the forced convection, the non-dimensional number is Reynolds number, and since the boundary layer is associated, Prandtl number appears. Since in the heat transfer it takes place over the surface, there will be a formation of boundary layer. That's why Prandtl number comes into picture. It is a strong function of Prandtl number and Reynolds number, because forced convection is dictated by Reynolds number. Okay, force flow. Now Nusselt has a functional correlation like this: A Re to the power B, Prandtl to the power C, where the values of A and B you can see. Now for air flow over circular cylinder, if this is the thing for a circular cylinder, why you are taking circular cylinder, our configuration is like this. If this is the fin, flow is taking place perpendicular to this plane. Have you understood the bottom figure? The figure even in the bottom. If this is the fin, flow is taking place perpendicular to this plane. It means flow is about the circular part. Have you understood? Flow is taking place in this direction. This fin is perpendicular to this plane. It means it is a flow past cylinder kind of thing. Now this is the correlation. Nusselt is this, Reynolds number is this. So here rho Vd by mu, so velocity is defined as volume flow rate by area. Now if you can determine volume flow rate, and if there is a duct, in this setup there is a duct and fin is there. So if you can determine Q, volume flow rate of air, you can determine velocity. Now I would like to ask you one question. Seeing this, you may ask me, sir, why Prandtl number is not there in these two relations? Can anybody answer?
Sir, if we keep Prandtl number constant.
See, here it is written for air flow over circular cylinders. When you fix air, since Prandtl number is fixed for air, our Prandtl dependence is not there. Have you understood?
Yes, sir. Yes, sir.
When you use the correlation in this generic form, this is true for every fluid. Each and every fluid. It is valid for a wide set of fluids. But when you fix the typical fluid, since the property Prandtl number is fixed, now there is no dependence on Prandtl number. It is dependent only on Reynolds number. Have you understood? So when this kind of correlation is used, this is independent of fluid. Take the fluid, check the Prandtl number, put it here in the correlation. But these correlations is developed for air only, for a fixed Prandtl number. Okay. Have you understood?
Yes, sir.
Yes, sir. Yes, sir.
Now coming to determination of Q. volume flow rate of air. Here also some concept of fluid mechanics which is already covered in your course. So this is, if you consider here, there is a orifice meter. So this is the orifice plate and there is a flow taking place in this direction. So you can see due to this, in the U-tube is put here to measure the pressure drop. So there is a pressure drop here, pressure drop takes place and due to this velocity increases. Okay, so if you apply the Bernoulli equation here, so you can write P1 plus half rho A is the density of air, V1 square in this section will be equal to P2 plus half rho A V2 square. Secondly, if the density remains constant, you can apply the continuity equation, 1D continuity equation like A1 V1 equal to A2 V2, volume flow rate will be constant. Okay, so by use of these two equations, you can first of all V2 square minus V1 square, you can see from this equation. First of all, this is V2 square. If you take common this, then this will be equal to 2 into P1 minus P2 by rho A from this equation. Okay, you can see here 2 into P1 minus P2 by rho A. This will be equal to V2 square minus V1 square. So this will be P1 minus P2. If you put a U-tube manometer here and you put water here, this is the head. Basically, this is the pressure drop as shown by the this head difference. Okay, so this is the pressure drop across this orifice. Now P1 minus P2 is rho Hg. C suffix is W because water is used here. So you are putting density of water, rho W, HW into G. Rho GH is the delta P. So you put it here, V2 square minus V1 square is coming as 2 rho W by rho A HWG. Okay. Now, how to determine volume flow rate? Volume flow rate, you can see along this section, if this is area, this is known as vena contracta. You have studied in fluid mechanics. This is the minimum area of the streamlines here. So this is the vena contracta area. So this is the velocity V2 and volume flow rate is given A2 into V2, area into velocity. Now this is A2 is replaced as coefficient of contraction since there is a contraction into A0. A0 is this orifice area into V2. Okay. So here, if you substitute the expression of V2 from here, so you will get Cc into A0 into this. Okay. Because V2 is V2 square minus V1 square equal to this. So V2 square into 1 minus A2 by A1 whole square equal to this right hand side. So naturally, what happens to V2? V2 will be 2 rho W by rho A HWG into A1 square by A1 square minus A2 square. Now here there is a square. So we are taking square root because here it is V2. So this will give me the flow rate of air. Now see, Cc into this factor root over A2 square, A1 square by A1 square minus A2 square. This one is together is basically CD, which is coefficient of discharge. Okay. So this is CD. So it comes as CD into A0 into root over 2 rho W by rho A into HWG. Is this clear how to determine volume flow rate? So we have in this setup there is an orifice plate. So through this orifice plate we can determine the volume flow rate. You have seen that how we apply the fluid mechanics principle and there is a recap. So this can be determined. Now coming to experimental setup. See here, first here this figure. See at the bottom there is a duct. Rectangular duct is there. You can see this is the inlet of the duct. Okay. So here there is a fin here. So fin is basically inside this duct and there is a heater which is heating the fin material from the base. So it is electrically heated and there is a blower here. This blower is basically run by a motor, electrical motor, and this is basically sucking the air from this side. Okay, so this air will come, okay, come, and it will be moving in this direction. Okay, so orifice plate is put here, and there is, you can see, two pressure tapping point along which you can measure the pressure drop, and you can flow what is the volume flow rate, okay, which is moving through this. Okay, you can see this is the enlarged view across the orifice plate. Okay, and this is the manometer. Manometer is enlarged here. Okay, across this orifice plate. Okay, you can see here 1 voltmeter. So basically this heater is attached with the electric thermostat. Okay, there is 1 ammeter and 1 voltmeter. So basically you can see this thermostat here. This is a variac control. So putting this variac, you can you can increase the voltage and current. So through this voltage and current, this heating will be controlled. Okay, will be controlled. Okay, and there are some thermocouples. You can see some wires coming out here. These thermocouples are attached to the different location, different axial location of the fin. From here you cannot see the fin. Fin is inside this basically inside this panel. Okay, inside this chamber fin is there. So it is perpendicular. Fin enters perpendicular to this plane, and through this duct air is passing perpendicular to fin, as if the air is passing through a circular tube. Okay, circular basically cylinder. So it is the cross flow. Air is passing cross the tube. Okay, it is not axial flow. Have you understood the configuration?
Yes, sir. Yes, sir.
Now there are 6 thermocouples. 5 thermocouples are attached at the axial location, different axial location of fin. 6th thermocouple is there to see the ambient temperature. Okay. Now here there are temperature scanner. So from here you can see the different temperatures are displayed here. So you know, when you actually students do physically the lab, they can stand in front of the setup, see all the components. Not only that, they run the setup, they take all the data from here. Like here, voltmeter will give the voltage, ammeter will give the current. From here we can calculate how much is the heat transfer, power input. Power input is basically Q is that voltage into ampere. Then from this temperature scanner you can select the switch, and you can see T1 to T6, T1, T2, T2, T3, T4, T5. These 5 temperatures are denoting the temperatures of different axial location of fins. T6 denotes the temperature of the ambient. Okay. So that's all about the setup. Now coming to, you can see this sketch is given here. Yes.
Sir, ammeter and voltmeter can also be used to increase the electrical power supply to the blower.
Electrical power supply can be increased because this is the thermostat. You can see by changing this knob, rotating this knob, you can increase the voltage and power. Because voltage, when you will change, the current is automatically changed.
Yes,
because the resistance is fixed here. Okay. So
sir, blower যে velocity-টা মানে এয়ার যেটা পাস করছে
ব্লোয়ারের ভেলোসিটিটা আমরা ভালভ দিয়ে কন্ট্রোল করি।
ওকে,
এখানে একটা ভালভ আছে, এই ভালভ দিয়ে কন্ট্রোল করা হয়।
ওকে,
স্পিড কন্ট্রোল নয়, ব্লোয়ারের পাওয়ারটা ভালভ কন্ট্রোলড। ওকে,
ওকে স্যার,
নট স্পিড কন্ট্রোলড। You know na that either you can, by changing the valve opening of the blower, you can change the flow rate. So here changing the valve, you can change the flow rate.
Okay sir.
Okay.
Yes sir.
Fine. You can see this is the sketch. So this is the fin. You can see heater terminals are here coming. It is wrapping the fin. The heater is basically put it here, and this is giving the power input. You can see the terminals, heater terminals here. plus and minus, you can see. And here, this is the base of the fin. So at different locations, 1, 2, 3, 4, 5, the thermocouples are mounted, and here the locations are also given. Okay. And you can see this is the sketch of the setup. Okay. So this is the blower, this is the duct, air is coming, entering. Okay. So this is the duct, and fin is mounted here perpendicular to this duct, so such that the air flows past the fin. Okay. It moves in this direction. Okay. Here there is the orifice plate. There is the U-tube manometer is there. Here there is the thermostat. Okay. And here the selector switch from which you can see the temperature. Okay. These are some of the specs which you may require during calculation. So I will later send you a lab sheet sample calculation, because right now, you know, under the pandemic, you don't have the opportunity to take the run and take the data on your hand. So rather I will send you a lab sheet from which you will try to see the data and try to write the report accordingly. Okay. So these are the typical specifications which are given for this particular setup. Length, diameter of the orifice, coefficient of discharge. Okay. All the make, centrifugal blower with motor, these makes are the apparatus make, all these name, these are given. Okay. Thermocouple spec, then temperature indicator, what is the voltage range. These are the specs, you know, normally in any lab sheet the specs are to be filled. Okay. So you can see here. So here keep one thing in mind, here kilocalorie is given. Please change in the unit, in the SI unit. Whatever you will change, you change in watt or kilowatt, whatever in the consistent unit. Don't use kilocalorie. Okay. That may be a problem for you to calculate. Okay. Procedure. Start heating the fin by switching the heater and adjusting the thermostat voltage to a specific value. Start the heater. Start the blower and adjust the difference of level in manometer to a specific value with the help of a valve. There is a valve. So you adjust this value. This value you adjust. Similarly, this voltage also you adjust. When steady state is reached, very important, very important. If you take the data when it doesn't reach the steady state, the entire calculation will be erroneous and you will get wrong the result which is not correct. So you have to wait for steady state. How you will understand whether it will reach the steady state? You see the reading, T1 to T5 reading, and check with time a particular, say suppose T1, you fix at T1, wait for some time, see with time whether T1 is varying. If the variation is within 0.2, 0.3 degree, then it's okay. Okay. Okay, 0.1, 0.2 degree. But if the variation is much more, they say 2 degree, 1 degree, please wait for that. Because the system takes some time to reach the steady state. Okay. So, when steady state is reached, record the final readings T1 to T5 and also recording the ambient temperature. Then, repeat the experiment with different values of HW, put up the main switch. So, have you understood? Very simple experiment. First, switch on the heater, start the blower. So, heater you give the specific thermostat voltage and ampere, take the reading, start the blower, manometer reading, adjust the level to a specific value, wait for the steady state. After steady state is reached, record the final readings, repeat the experiment with different values of HW. Okay. Precautions: never exceed the heater voltage more than 120 volts, that is the limit. See that the thermostat is at 0 before switching on the heater. Okay, this is very important. Be sure the steady state is reached before taking the final readings. Now this is the observation table. You can see these locations are given in the data is given. So you first note this voltage, then the manometer reading, steady state temperature, then ambient temperature. So here calculation, fin temperature, first calculate fin temperature. You can take the mean of these 5. Mean film temperature is based on, what is mean film temperature? Can anybody answer? Mean film temperature. Are you there?
Yes, sir.
Yes, sir. We don't know what is mean film.
Janina, sir.
See, any surface when fluid is flowing, you will find in many correlations there is the surface temperature. See, the fluid is at surface temperature and there is a free stream temperature which is T infinity. So usually these correlations are given in many occasions. You will find the properties are taken at mean film temperature. Like I am giving you one example. You want to write Reynolds number. What is the expression of Reynolds number? Tell me.
Rho v d by mu.
Rho v d by mu. So here mu, which mu you should take? Suppose your surface temperature is say at 100 degrees centigrade and your free stream temperature is say 25 degrees centigrade. It means within the thin boundary layer there is a temperature variation between 100 to 25. So rather than taking that property at a fixed value, you take the mean film temperature, that is 100 plus 25 by 2. It is sensitive to that data. Have you understood?
স্যার আরেকবার বলুন স্যার।
স্যার মানে এখানে কি অ্যাভারেজ নিচ্ছি?
অ্যাভারেজ নিচ্ছি।
অ্যাভারেজ কার সঙ্গে?
and the free stream temperature, তাই তো?
আমি ধরো ভিসকসিটির ভ্যালু নিচ্ছি, which is a function of temperature.
Yes, sir.
ধরো আমি এয়ারের ভিসকসিটি নিচ্ছি, রেনল্ডস নাম্বার ক্যালকুলেট করছি। তাহলে রেনল্ডস নাম্বার ক্যালকুলেট করার সময় কি হবে? রো ভি ডি বাই মিউ। ভিসকসিটি আমি সারফেস টেম্পারেচার যদি 120 ডিগ্রি হয়, ওখানে এয়ারের টেম্পারেচার কত? সারফেসে এয়ারের টেম্পারেচার তাহলে 120 ডিগ্রি।
হ্যাঁ স্যার।
আবার এয়ার যখন ফ্রি স্টিমে আসছে, এইটা তো হচ্ছে খুব স্মল ডিফারেন্সে, এটা তো খুব স্মল একটা লেয়ার। বাউন্ডারি লেয়ার যেটা সেটা তো খুব স্মল লেয়ার, তাই না?
Yes, sir.
হ্যাঁ স্যার।
Say that temperature is 20 degree. Now see, if you see that the viscosity is very sensitive to this temperature variation, what will you do? Which temperature you will take? So here very often you will find this is called mean film temperature. In this temperature you will take the property data. This is required for the property data.
Okay, sir.
Area of orifice this, calculate the volume flow rate. Volume flow rate we have already seen. Velocity of air at TF. You see here how we are using mean film temperature. Velocity of air at TF. This is velocity of air at TF, ambient condition. This is Q by area of the duct. Duct area is different, okay? Don't confuse this duct area with this area. Remember, this area is orifice area. This is the duct area. Duct area মানে কি? আমার এইখানে velocity কত? I will try to find out what is my velocity here near the fin. When we are considering the flow through this, we are considering A0. But here, if I want to calculate velocity here, because unless I calculate velocity, I cannot determine Reynolds number. Is it clear?
Yes, sir.
Yes,
So here, if you consider the volume flow rate here, this volume flow rate is at this temperature TF. But here the temperature volume flow rate, when we calculate near the fin velocity, okay, near the fin we try to calculate the velocity. Then what happens? We have to calculate it at this. So VMF is equal to VF into TMF plus 273.15 by TF plus 273.15. How this formula is arrived? Can anybody tell? This is basically, you can say, I am calculating velocity. Okay. So volume flow rate. So this is kind of, ideal gas relation kind of thing is utilized here. What is the velocity of air at TMF? Have you got it?
No, sir.
No, sir.
No. আচ্ছা পিভি, আচ্ছা আমি একটু ক্লু দিচ্ছি, এবার একটু তুমি কনভিন্সড হবে কিনা জানি না। পিভি ইকুয়াল টু এমআরটি তো?
হ্যাঁ স্যার।
আমি যদি ভিটাকে ভি ডট বলি কি হবে? ভলিউম ফ্লো রেট হবে তো?
Yes, sir.
Yes, sir.
ভলিউম ফ্লো রেট যদি পার ইউনিট টাইম, এটা তো একটা ভলিউম অফ এয়ার। পার ইউনিট টাইম ইট ইজ আ ভলিউম অফ এয়ার, রাইট? হুইচ ইজ অ্যান আইডিয়াল গ্যাস।
Yes, sir.
তাহলে এটাকে যদি আমি রিলেট করি, পিভি ইকুয়াল টু এমআরটি, ইট ইজ প্রপোর্শনাল টু টি, কিপিং আদার প্যারামিটারস কনস্ট্যান্ট।
Yes, sir.
তাহলে হোয়াট উইল বি মাই ভেলোসিটি অফ এয়ার এট টিএমএফ? VMF will be VF into TMF plus 273.15 by TF plus 273.15. Isn't it?
Yes,
Now
sir.
you may wonder why we are considering this. এই জন্যই হিট ট্রান্সফারটা পড়তে হবে, বাউন্ডারি লেয়ার একটু পড়তে হবে। এখানে কি বোঝা যাচ্ছে না? আর একটু ইলাবোরেট করতে হবে, বলো। তাহলে করবো,
Yes,
বল।
sir. Understood.
Have you understood? See, what is happening? Near the surface, there is a thin film, boundary layer film. Near the surface, temperature is something, and free steam temperature is TF, and TMF is the mean film temperature. Now, this velocity I have calculated near orifice TF. This VF is at TF temperature. Now, what will be my velocity at T mean film temperature? Why T mean film temperature I am considering? All the properties are considering at mean film temperature. Okay. Okay.
Okay, sir.
Now, if this velocity is known, then you can calculate this velocity is known. You can calculate Reynolds number.
Reynolds number.
Once you know Reynolds number, you know also Prandtl number. You can calculate Nusselt. Nusselt equal to this. You substitute here. Then HD by KF. From here you will get H. Once you know H, you will put it here. You will find the temperature distribution, because M is M square equal to HP by K. Substitute or 4H by DK. Put it here H. Now M is known. You can calculate temperature distribution. You can calculate rate of heat transfer. You can calculate fin efficiency. All the parameters. Is that okay?
Yes, sir.
Yes, sir. Yes, sir.
Results. Plot temperature distribution along the fin. Experimental temperature distribution. Calculate the fluid properties at TMF. কি বললাম? এটা বোঝা গেল?
হ্যাঁ স্যার।
কি বোঝাছো বলো?
স্যার সব প্রপার্টি গুলো মিন ফিল্ম টেম্পারেচারে নিতে হবে অ্যাকচুয়ালি।
মেইন ফিল্মে কেন নিচ্ছি? বোঝা গেছে?
হ্যাঁ স্যার, কারণ সারফেসে একটা টেম্পারেচার থাকে আর ফ্রি স্ট্রিমে একটা টেম্পারেচার থাকে।
Right. Now calculate Reynolds number and Nusselt number. Calculate Reynolds number and Nusselt number. Once I know the fluid properties at mean film, I can calculate Reynolds number because I know the velocity and all the properties. Rho Vd by mu. তাহলে রোটা আমি মিন ফিল্মে নেব, মিউটা মিন ফিল্মে নেব, রো Vd by mu, velocityটা মিন ফিল্মে নেব। Okay. Now I know Reynolds number, I calculate Nusselt number. Now again in Nusselt number, what is the expression of Nusselt number?
HD by K.
এখানে kf টা কি নেব? থার্মাল কন্ডাক্টিভিটি
এর জন্য।
এয়ার কোন টেম্পারেচারে নেব?
স্যার মিন ফিল্ম টেম্পারেচার।
রাইট। কেউ বুঝতে না পারলে আমাকে ইন্টারাপ্ট করো, আই উইল এক্সপ্লেন এগেইন। Now from this, calculate heat transfer coefficient H, rate of heat transfer and fin efficiency. Obtain theoretical temperature distribution assuming insulated tip. Insulated tip এর জন্য theoretical temperature distribution ওই H টা ধরে নাও, ওই H আর ওই P সব ডেটাটা নিয়ে নাও। ওই ডেটা নিয়ে তুমি যেটা করো, you will find this is your theoretical. Once you put the value of M here, তুমি তো H টা নিয়েছো, H আর সব ডেটা নিয়ে নাও, দিয়ে থিটা প্লট করো। Theoretical value will give this one. তুমি এক্সপেরিমেন্টটা কি পেলে প্লট করো একই অ্যাক্সিসে, বুঝতে পারছো? Have you understood? First you calculate your experimental data. Second you calculate this theoretical data theta as a function of x. Plot theoretical data which you are getting from analytical solution. Then you plot your data which you determine from experiment. Experiment মানে তুমি এক্সপেরিমেন্ট কোথা থেকে পাচ্ছ? এই টেবিল থেকে যেটা পেয়েছো, এই টেবিল থেকে যেটা পেয়েছো এটা এক্সপেরিমেন্টাল ভ্যালু। এই টেবিলে যেটা পেয়েছো ওখানে কোনো ক্যালকুলেশন করেছো? হ্যাভ ইউ ডান এনি ক্যালকুলেশন? নো। What you are getting from experiment. Okay.
Okay, sir.
Show all the steps for one run as sample calculation. এখানে যতগুলো স্টেপ, all steps should be given as sample calculation. Plot theoretical and experimental temperature profiles for each case on the same graph. Fluid properties data are given here. It is not very clear. You can see any heat transfer book appendix, you will get all the data. Okay. Observation table, sample data, এটা স্টুডেন্টদের আমরা স্যাম্পল যে স্টুডেন্টরা করে এখান থেকে ডেটা নিয়েছি। আনফরচুনেটলি তোমরা এখন করতে পারছো না, আমি জানি না কবে যদি কলেজ খুলে আমরা যদি একটা দুটো এক্সপেরিমেন্টও পারি, অ্যাটলিস্ট আমি চেষ্টা করব তোমাদের নিয়ে গিয়ে এক্সপেরিমেন্ট করাতে কিছু। হ্যাঁ, অন্তত আমি যদি দুটো তিনটেও করাতে পারি তোমাদের ধরে, হ্যাঁ, তাহলে এগুলো এক্সপেরিমেন্ট গুলো তোমরা কোড করতে পারবে আর কি। That's all. Now if you have any doubt you can ask me or any query. Have you
the expression?
Yes, Abhishek.
So in the expression for Nusselt number, we saw that Nusselt number was only a function of Reynolds number. So for a wide range of Reynolds number, in that case, we will observe that Nusselt number will be less than 1 actually, greater than 1 actually. So sir, if we analyze it like convective heat transfer to the conductive heat transfer ratio.
Okay. Now what do you mean to say? See here what I said. Generally in forced convection, not generally, it's true. For always forced convection, Nusselt number is a function of two parameters, Reynolds number and Prandtl number, right?
Yes, sir.
For simple geometry, I am talking about simple geometry. Now Reynolds number and Prandtl number. Now question, ask me. What do you mean to ask?
Sir, in that specific case, we saw that Nusselt number became a function of Reynolds number only because we fixed the fluid to air.
No, we have selected air only.
Yes, sir.
We have got the correlation for air only. Now, when we are selecting, putting the regression analysis, these are obtained from regression data. Regression data means you do wide level of experiment. Okay. After you do the experiment, you fit the curve. After fitting the curve, you minimize the error. Now, since you are doing the experiment with air only, Prandtl number doesn't vary. Only parameter varying is Reynolds number. So
Yes,
naturally, only Reynolds will come. But when you are putting as a function of two parameters, it is true for all fluids. That is a big data.
Yes, sir. Sir, in that formula, for a wide range of Reynolds number, we will observe that Nusselt number is greater than 1 for a wide range of Reynolds number. So Nusselt number becomes the ratio of the convective heat transfer to the conductive heat transfer. So from there, we can obtain that convective heat transfer for a pin will always be greater than the conductive heat transfer. Sir, is this analysis valid for all fins?
See, there are many things has to be said here. I'm talking about one thing, like this can be shown. See here, of course, convective heat transfer is greater than conduction heat transfer, and in the limit when convection heat transfer is 0, you will have only conduction component. Okay. So normally, there is some scale analysis kind of thing. I can show you. If you are interested later, we can discuss on this. Like over a sphere, if you have a flow over a sphere, you have this kind of correlation. Nusselt equal to 2 plus Reynolds to the power something, Prandtl to the power something. Means at the limit of Reynolds number 0, Nusselt number becomes 2, equal to 2. This 2 factor comes when it is solely conduction. Have you understood?
Sir, but in the case of flow past a sphere, the Reynolds number will be very high.
No,
If it is laminar. For
depends on the flow over the sphere. Reynolds number is dependent on so many parameters. How is the
So it
how
will remain
big is
laminar.
the size of the sphere? What is the velocity? What are the properties?
yes, sir.
Like for air, 10 meter per second. For water, 10 meter per second may give some Reynolds number, but for air it will be very less because density ratio of air to water is something like less than 100, something like this. Okay, means. It is not dependent on that parameter only. Okay, what you are saying is correct, that convection heat transfer. See, the thing is, there is some part of conduction, some part of convection, but these things take place simultaneously, and of course, the magnitude of convection under all practical scenario is much higher than conduction.
Yes, sir. So convective heat transfer will be more than conductive heat transfer in this case. So, sir, instead of increasing the length of the fin, we can increase the area of the fin in lateral direction. That will become more effective because we know that convective heat transfer is going to be greater than the conductive heat transfer.
See, that you have to need analysis. I don't know whether that we can conclude from this, to think about it, what you are saying. Basically, you have to see the fin effectiveness. If you see this formula, one thing is true that this may not be valid for this thing always, but you see here, in the fin effectiveness, this parameter you have to see the effectiveness. You are talking about fin efficiency or something like this, efficiency?
No, sir, the Nusselt number calculation. The Nusselt number becomes a ratio of convective to conductive heat transfer. So, sir,
See,
here in this formula.
is the ratio of convective to conduction heat transfer.
Yes, sir.
That is.
Sir, in the second case, you wrote that Reynolds number is between 4,000 and 40,000.
This is not a true thing. Nusselt number is a ratio of conduction to convective heat transfer. This is not the thing. I will discuss later. This is a very simplification. The meaning of Nusselt number is not like that. Okay.
Okay, sir.
Convection to conduction is not like that. See, the thing is like this. If we have a surface and we have a fluid flowing over this, how this Nusselt number comes up, this two ratio H and Kf? Have you thought about this? Why these two ratios are coming here? Think about it. If there is some flow takes place and this is a hot object, under steady state, whatever heat is conducted from the surface, that will be convected through the surface under steady state. Have you understood?
Yes,
From
sir.
the surface to the fluid, see what happens. The fluid immediately at the wall is attached to the wall, so it doesn't move with the wall. It is attached to the wall due to this viscosity effect. In the boundary layer, it's called no slip boundary condition. It is attached to the wall. Now what happens? From the wall to the layer, fluid which is immediately attached to the wall, since fluid is immediately attached to the wall, it means fluid does not have any motion. Isn't it?
Yes, sir.
Now, if the fluid does not have any motion, what is the mode of heat transfer? Tell me.
It's a conduction only.
So, this is moving by conduction. This term is coming of this Kf from here, from Kf from here. Now, this heat is convected by the motion of this fluid packet, okay, which is moving by. Under steady state, this is happening always. Have you understood? So it is happening like this balance. Whatever is conducted from this surface is convected. Now what happens? when I am increasing, suppose I am keeping the same temperature, now I am increasing the velocity, then what happens? The capacity to convection is increasing. Now this balance has to be maintained because temperature has to be constant. Now conduction will be also increased.
Yes, sir.
Okay. So Nusselt number is a ratio of convection and conduction. It is not, probably not true. Okay, like HD by KF. From here, if you multiply by, secondly, this KF is the thermal conductivity of fluid. Okay, remember, this is not the thermal conductivity of solid. This is the thermal conductivity of fluid. So I am increasing the velocity, I am increasing the turbulence, the energy taken, since I am increasing the advection part, this is called advection. This motion I am increasing, so capability increases. Naturally, more energy will be convected. So from the wall also it will be more conducted. Have you understood?
Yes, sir.
That balance has to be maintained. Otherwise, how the steady state will be maintained? Tell me.
Understood, sir.
Related to this, we may discuss more later. Okay, we may discuss related to this issue. Maybe during convection we will discuss more. Acha, tell me if you have any other question by somebody. So hope you have understood. Now in the next week we will discuss about the second experimental setup. So maybe after 2 or 3 classes you can send one by one assignment. So maybe 2 assignments you can send. I will create a Google Classroom. So I will upload the video and I will send you the requisite materials. So you can start doing the lab report, or if you want that, no, sir, give us some time, at least 15 days, then you can start from that day also. Okay. Maybe after completion of 2 experiments, then you can start. Whatever you feel comfortable, that will be okay. Any query? Okay. Thank you, everybody. Take care. Stay safe.
Thank you, sir.
We'll meet again.
Thank you, sir. Thank you, sir. Thank you, sir. Sir, the attendance today.
Attendance, someone has to take responsibility. Who is the CR?
Sir, Ami, sir.
অর্ঘদীপ
হ্যাঁ স্যার
অর্ঘদীপ তাহলে আমাকে একটা এক্সেল শিট পাঠিও বাবা। হ্যাঁ
ওকে স্যার ওকে
আমাকে মেল করে দিও প্রত্যেকটা ক্লাসের পর। তুমি জাস্ট এক্সেল শিট, এখান থেকে তো এক্সেল শিট জেনারেট করা যায় বোধহয়, দেখো।
হ্যাঁ স্যার হ্যাঁ স্যার
হ্যাঁ, তুমি ওইটা আমাকে পাঠিয়ে দেবে প্রত্যেক ক্লাসের পর। ওকে
ওকে স্যার
থ্যাংক ইউ ভেরি মাচ।
ওকে স্যার।